In chapter number 9, we're going to discuss some other optimizer operators. After you have completed this lesson, you should be able to describe the result cache operator, and you should also be able to describe other SQL operators like clusters, enlist, sorts, filters, and set operations. The first SQL operator that is being discussed within this chapter is the so-called result cache operator. Now, the result cache is an area of memory, either in the SGA, the System Global Area, or the client's application's memory, that stores the result of a database query or query block for reuse. So you have the possibility, whenever result caching is enabled, you have the possibility to store the results of an SQL query in memory. If then that same query is going to be launched again, and the underlying data in the access table did not change, the query no longer needs to access the data stored in blocks, so it doesn't have to access any blocks anymore, but it can get the result directly out of memory, in fact. So this will reduce I/O operations as well blocks being accessed inside the database. Let me first show you an example of the result caching, in fact. I have here my practice environment where I've already set up a demo showing you the effect of result caching. Now, first of all, result caching must be enabled, in fact. And you can see that at that moment in time, the status of my result caching is bypassed. It means that result caching is not going to take place. So it means that if queries are being executed, to obtain the data, blocks need to be accessed in memory, or additional I/O operations are needed to upload blocks with the data needed into memory. Now, a DBer has a possibility to activate result caching by simply setting the parameter result cache max size to a specific value. Like here, I'm asking to reserve about 2 megabytes in the SGA for this result caching, in fact. So this is a parameter that you need to set. Yeah, but there are other parameters that will influence this result caching technique. One of them being the parameter result cache mode, which defaults to manual. This means that if I want to cache the result of a query, I will have to specify explicitly a hint that I want caching to take place, in fact. You can also put the parameter result cache mode to false. That means that for every query that I execute, I would like to store the result of each SQL query inside the result caching. But for my demo, I'm keeping the result cache mode parameter to a manual. Then what did I do is you have a package called dbms result cache, where a DBer can request a report on the memory utilization of this result caching technique, in fact. But this is not really the scope of this chapter. But what do you see is that there are also several views that you can take a look at, like VDOL result cache statistics. And what do I see is that up till now, already 4 results of select statements have been cached inside the result cache memory, in fact. Now, what do I have is, if I continue further in this demo, because my parameter result cache mode has been set to manual, and I want to cache the result of a query, I will be forced in that case to use a hint called result cache, in fact. So I'm stating, look, I want to obtain all the records of table departments in schema HR, but that result needs to be cached inside the result cache memory. Now, the very first time that you're going to execute that select statement, of course, that result is not yet cached, in fact. So the very first execution of a query of which you would like to cache the result has to be executed in the traditional way by accessing blocks and filter out the records that are needed, in fact. But you see that I'm executing this statement, in fact. I'm getting my records back, getting my results back. And if you take a look at the execution plan, you see that the result cache SQL operator is being shown. Now this can mean two things. Or the result of this query has been cached inside the result cache, or the data that was returned comes directly out of the result cache. In fact, now how can you see if the result cache operator indicates I have cached your results or I have retrieved your result from the result cache? Well, if you take a look at the execution statistics, you actually see to perform that select statement, although decorated with the result cache hint, in fact, that it has access blocks, because I'm seeing that the sum of db block gets and consistent gets is not 0, in fact. So it actually, in a traditional way, has access blocks to get that data, in fact. And you will see, for instance, if I'm asking for the VDOL result cache statistics, in fact, you see that my create count success went up from 4 to 5 because that result of my last executed select statement upon table departments of HR has been cached, in fact. Now, what I'm going to do then is, I can ask for my memory report, but that is out of scope for this course, in fact. But now I'm going to execute that same select statement again, of which at the first run, the result was cached inside the result cache zone, in fact. Now look what you get is, you get this same result, in fact. You see in the execution plan, the result cache operator, in fact. But once again, you cannot see, okay, this result that I'm getting, is it now being cached in the result cache? Or has it been retrieved from the result cache? Well, if you look at the execution statistics, you see to obtain that result of that select statement, you see that the sum of db block gets and the sum of consistent gets, that this is 0. So that means that to obtain that result for that second execution of that select statement, Oracle did not access any of the blocks. No, he saw that that result of that select statement is still in a consistent state, but that result is already inside the result cache, in fact. So this tells me that the result came out of the result caching memory, in fact. And this will, of course, speed up, as of the second execution of that select statement, it will speed up the response time, in fact. So that is your result caching, in fact. So if your parameter result cache mode is set to manual and you want that the result of a query is being cached, you have to use the hint result cache, in fact. You will then also see the result cache operator appearing in the execution plan. If you know which VDOL views to access, you can obtain information about the results of which queries that are cached inside that result cache, in fact. But you have to use hints, in fact. You can also say select no result cache. So use the hint no result cache means I don't want to cache the result of this query, in fact. However, what you can do is you also have the possibility to use table annotations to control result caching, in fact. And with those table annotations, you can avoid the necessity of adding result cache hints to queries at the application level. So for instance, you can see that the creation of this table sales, I've decorated it with the result cache table annotation, and I gave it the value mode default, in fact. And mode default means if at least one table in a query is set to default, result caching is not enabled for queries happening upon this table sales, unless the parameter result cache mode has been set to force, in fact. However, if you would create your table, or you alter your table to change the result cache to, let's say, mode force, in fact, mode force table annotation means that if all the tables of a query are marked with result cache mode force, the query result is considered for caching, in fact. So the force table annotation forces the database to cache the results at the table level, in fact. So that was the result cache operator. Then you have the cluster operator. Now, what you have is, I think everybody knows what tables are. Yeah? Most commonly used table structure are the heap organized table. Yeah, you create a table, it allocates space. That space is divided into blocks, and it's in those blocks that the records are going to be stored. In fact, yeah, they are being put upon a pile, in fact. However, there are other types of tables that can be used, in fact. One of them being clustered tables, in fact. So clusters are an optional method for storing table data. So let's say, for instance, that you have a table orders and you have a table order items. You can store both tables as separate objects. But we do know that an order consists of order items, and an order item is always part of a particular order. So orders and order items is data that logically belongs together, yeah, but it's stored physically separate from each other, in fact, yeah, because you have two unclustered tables. Now, if you have data that logically belongs together, like orders and order items, you have the possibility to cluster the data of orders and of order items. That means that you can store logically related data also physically together, but still having the concept of having two tables, orders and order items, in fact. And the thing is now, because now data is being stored physically together that logically belongs together, in fact, if then queries are going to be executed and you want to find out, can you show me order 101 and all of its order items, I do not have to scan two different tables to obtain the result. No, I only have to scan the cluster that holds the data for the tables orders and order items, in fact. So a cluster is a group of tables that share the same data blocks because they share some common columns and they are often used together, like in this case the orders and the order item tables, in fact. Now you have different type of clusters that you can create. You have on one hand the index clusters, yeah, and that's especially being used for tables that are always joined on the same keys. Also, if you don't know the size of your table, and it can be used in any type of search, it can be used for equality as well as for non-equality searches, in fact. A hash cluster is used for tables that are always joined upon the same keys. Storage for all cluster keys is allocated initially, in fact. Can be used for equality and non-equality searches, in fact. You can also create single table hash clusters, which is actually a very fast way to access a large table with an equality search, in fact. You can also create sorted hash clusters, which is used only for equality searches. Now, reading upon a normal heap organized table or reading upon a cluster table, that's exactly the same syntax, in fact. So your application code will not change. It's only the underlying method for storing the data that is being changed, but not the application code itself, in fact. Reading upon a normal table or reading upon a cluster table requires exactly the same syntax, in fact. But you will see, for instance, that whenever you're going to access cluster tables, in fact, that in your execution plan is going to show you information that a cluster is being accessed, in fact, or that a hash cluster table has been accessed, in fact. So that is the story about the clusters, in fact. Then you have the sort operations. Now, I think that everybody knows what an order by clause is. It's the very last clause that you can put in a query, in fact, because you want that the returned result is being sorted in a certain way, in fact. Yeah, but there are also other sort operations. Like, for instance, you have the sort unique operation. And that's an operation being used to remove duplicates. That's something that you will see pop up in your execution plan whenever you're going to use the distinct keyword, in fact. If you see a sort join, in fact, this means, as discussed in the previous chapter, that you're joining two tables together with the sort merge join method, in fact. So the thing is, that there are SQL operators like sort aggregate, sort unique, sort join, hash group by, hash unique, in fact, that will induce sort operations. Not necessarily explicit sorts. If you type in an order by, this is an explicit sort, but if you say, I'm going to use the distinct keyword to remove duplicates, well, he does a sorting because out of a sorted list, it is much easier to remove the duplicates, in fact. So several sort SQL operators are done implicitly, in fact. Now, if you want that the results are always ordered in a specific way, you always have to explicitly use the order by clause. Then you have the so-called buffer sort operator, in fact. Now, the buffer sort is not a sort operation, in fact. No, the buffer sort operator uses a temporary table or a sort area in memory to store intermediate data. But like I've said, the data is not necessarily being sorted. The buffer sort operator is needed if there is an operation that needs all the input data before it can start, like for instance with a Cartesian join, in fact. So the buffer sort uses the buffering mechanism of a traditional sort, but it does not do the sort itself, in fact. Now, if for the execution of a query the buffer sort operator is being used, in fact, this will pop up like buffer sort operation within your execution plan. Then you have the inlist operator, in fact. The inlist operator that is being used whenever a query contains an in clause with values or multiple equality predicates on the same column are linked with the OR operator, in fact. So the inlist operator iterates over the enumerated value list and every value is executed separately, in fact. So you see my query is using the in operator. Well, you see here in my execution plan that the inlist iterator has been used. Then you have the view operator. The view operator is simply indicating that a view is being accessed directly, in fact. So first of all, a view simply gives a name to a set of data. Now, whenever views are being referenced in the from clause of your query, the system can handle them in two ways. If a number of conditions are met, that can be merged into the main query. This is the so-called view merging transformation technique that can be executed by the optimizer, which is something that we have discussed in the chapter about the optimizer fundamentals, in fact. However, views can also be left as standalone views and selected from directly as in the case of table, in fact. Now, whenever the view is being accessed directly, in fact, you will see the view operator appearing within your execution plan, in fact. Here they're using the hint no merge to indicate to the optimizer, look, you cannot apply the view merge transformation technique for this view, in fact. The next SQL operator that is being discussed is the count stop key operator. The count stop key operator, it will pop up as the stop key operator within your execution plan. You will see this in case in your select statement you're using the row num operator, in fact. The row num operator, also known as the count stop key operator, it limits the number of rows being returned. The limitation is expressed by the row num expression in that where clause. And this will terminate the current operation when the count has been reached. Then you have the min, max, and first row operators. For instance, you see here on the slide that they want to obtain what is the minimum value in the column quantity on hand, in fact. And let's say that you know that the quantity on hand column, that it has been indexed, in fact. that it has a B3 index. Now, as we have seen in one of the previous chapters where we discussed indexes, in fact, a B3 index is a sorted object. Yeah, the index entries that are being placed inside an index are being sorted by default in ascending order, in fact. So that means that in an index, the very first value stored inside the index, that's by default always the lowest value that is found in the column that you are indexing. While the last value that has been stored, that's always the highest value that is found in the column that is being indexed. So if you ask, I would like to find the min or the max value in a column, and that column is being indexed, it only has to read the first or the last value that is stored inside the index to know what is the minimum and what is the maximum value. And this will pop up as the operator first row, min-max operation, in fact. And then we have several other and array operations, in fact. You have filter, concatenation, union all, the union, the intersect, and the minus. Now these are operators that are explained in the subsequent slides, in fact. First of all, you have the filtering operation. Now the filtering operation is not really a row source operation of your execution plan. No, the filter operation is any operation that discards rows returned by another step in the execution plan. So it's not involved in retrieving data out of the table, in fact. Now, all sorts of operations can be filtered. Like in a full table scan, you can have a filtering operation, in fact. Also, when you perform subqueries, filtering can be performed, in fact. So a filter operation accepts a set of rows, eliminates some of them, returns the rest to the next row source operation within the execution plan, in fact. But you will see here if any filter predicates have been used, in fact. Like in that first example, the filter predicate sum salary bigger than 9,000 is actually a filtering that happens due to the having clause, in fact. Here the filter predicates, that's the join condition that is being defined in the where clause in this second example. Then you have the OR expansion operation, in fact. So you perform a select statement where you want to retrieve all the records where department ID is 10 or the location ID is 1700. Well, this OR operation here can be expanded into a union all, in fact. So what it's going to do is it's going to retrieve all the records where department ID is 10. It will retrieve also all the records where the location ID is 1700. And then those two result sets are combined together with the union all operation, in fact. And with that union, if there are duplicate records, duplicates will be suppressed. To avoid that, a record where department ID is 10 and the location ID is 1700, to avoid that it's being returned 2 times, in fact. So that's your OR expansion operation, in fact. The suppressing of duplicates happens via this function, the ln NVL function. To avoid that, a record where department ID is 10 and the location ID is 1700, that is being returned 2 times. Then if you use explicitly the set operators, you have union, union all, intersect, minus, this will be reflected inside your execution plan. Union, you're going to combine two result sets together, suppress the duplicates. Union all, you're going to combine two results together, but you will not suppress the duplicates. Intersect means only return those records returned by result set 1 and by result set 2, and also suppressing any duplicates, in fact. Minus simply means return all the records of one result set that are not being returned by another result set. To end this chapter, there are a couple of quizzes. The first quiz is that hash clusters are a better choice than index tables or index clusters when a table is queried frequently with equality queries. is this true or false? Well, the answer is true because hash clusters are indeed very good if the table is being frequently queried with equality searches. A second quiz is to complete a sentence. The operator uses a temporary table to store intermediate data. Is that the inlist, the min-max, the buffer sort, or the n-array operator, in fact? The right answer is C. It is the buffer sort operator to store intermediate data. The following query uses which operator? The buffer sort, the inlist, the min-max, or the n-array operator, in fact? This is of course the inlist operator, so answer B, because I'm using that in operator within my where clause. And then one last quiz. A filter operation retrieves the rows returned by another statement. Yeah, this is false, in fact. A filter operation does not retrieve data. No, it will only suppress data that is being returned by a rows source step within the execution plan. So the correct answer is false. So in this lesson, we have described several SQL operators like clusters, inlist, sort, filter, and set operators. And we also had a description of the result caching technique. The exercises of chapter number 9 will cover following topics, such as using the result cache and using different access paths for better optimization. These are case studies 13 till 15. Workshop 9 of the SQL Tuning for Developers course. So in this workshop, you will use SQL plan baselines to associate a hinted execution plan with a hard-coded SQL statements. This is a listing of all the script files that you need in this workshop. You can find them all underneath the workshops folder, and to make your life easier, open them all up beforehand. So Oracle has introduced several methods to maintain the stable execution plans of SQL statements, such as hints, stored outlines, and SQL profile. Now, in an Oracle database, you can manage the execution plan through a methodology called SQL plan baselines. This feature allows the optimizer to make the right decision, choosing a verified or tested execution plan in an SQL plan baseline, even if the optimizer generates a new plan during hard parse. So in this workshop, you learn how to use this feature to associate a hinted execution plan with a hard-coded SQL statement. Now, the first thing that you will need to do is you will have to run the script setup09.sql as the SH user to set up the environment for this workshop. So what you need to do is in SQL Developer, open your setup09.sql, choose the SH connection and run the script, which is going to create a table cost. It will create a bitmap index upon the customer's year of birth and upon the cost gender column of that table. So you have two bitmap indexes created, optimized statistics are being collected, and SQL plan management mechanism is active because the parameter optimizer use SQL plan baseline is true, and execution plans will be automatically captured because I've set the parameter optimizer capture SQL plan baselines also to true. Now, what we need to do now is we have to review the statement in the script WS09. This is a hard-coded SQL statement. This has to be tuned, but there are only a few options available to improve performance. So if I'm taking a look to the select statement, I'm reading the cost table, but I'm telling the optimizer to use the two bitmap indexes, the one upon the customer gender and the customer year of birth. Now, what you need to do is you will have to execute that statement and identify the SQL ID and the plan hash value using $SQL area view. You can do this by executing the script w9s2a.sql. So if I'm taking that script, this is where I can find that information. But what I will need to do first is I will have to first execute that statement. So I choose sh connection. I'm going to execute that statement. The select statement doesn't return any rows. We're only interested in the selection of the execution plans. And then what I can do is via the script w9s2a, I can then access SQL area to pick up the SQL ID as well as the plan hash value of that statement that I've just executed a couple of moments ago. So I choose sh connection. I'm going to execute this and I see the SQL ID as well as the plan hash value. So like I've said, the query does not return any value on purpose. It's only to see which plan can be used, which plan can be chosen. So here they carry out that script file to obtain the SQL ID and the plan hash value. Then we want to review that execution plan of that statement that I have executed. And you do this by running the script w9s2b that shows via the function display cursor of the package dbms explan the execution plan of that statement. I will need to provide the SQL ID. So I have here w9s2b, but here I will have to replace this by the SQL ID of that statement that I have executed previously. So I can find it back in that previous script file. I copy the SQL ID and I'm going to paste this into this function display cursor. Choose sh connection, execute the query. Now what do I see is that it's using a bitmap index and that it performs a bitmap merge operation of the two bitmap indexes that he's using, and the total cost of that select statement is 4. So the bitmap merge operation is used, the total cost is 4. Now what we're going to do is we're going to now load the execution plan of that SQL statement into the SQL plan baseline. We can use the script w9s2c to do so. So I have here my script file, but what I will need is I will have to enter here the SQL ID of that statement. So I can find this over here. I copy this. I'm going to replace this. Plus I also need to obtain the plan hash value of that statement. I can find that back over here. I'm going to copy paste it over here, choose sh connection, and I'm going to execute this. Procedure has successfully been completed. What I can then do is by running this script file, I can check if I have loaded that plan in the SQL plan baseline. So I'm using the script w9s2d, this script file, sh connection. I execute this and I see that for that statement that is using that hint index combined, that the SQL statement and its execution plan was uploaded into it. Then what we're going to do is we're going to re-execute that statement, but we're going to use another hint. So not index combine, combining the two bitmap indexes, but only to use the bitmap index upon the customer year of birth column. So I'm going to execute this and check the SQL ID and plan hash value. I can use the script file w9s3a.sql. So I have here w9s3a. I'm going to use the sh connection and I'm going to run the script. It's executed, the SQL ID and the plan hash value. Now, what we would like to do now is we would like to review that execution plan of that statement that is executed with this index hint. So I can use this script file, w9s3b, to display that execution plan, but I will need the SQL ID of that statement. So I go back to that previous script. I pick up here this SQL ID. I'm going to place this inside this select state. And I'm going to execute this. And the execution plan is being shown. And it's using only that index. And what do you see is that that bitmap merge operation is no longer being used. And that my total cost is only 2 compared to the total cost of 4 for that same statement, but using another hint. So the bitmap merge is avoided. The total cost is 2. That execution plan, we're now also going to load that into the SQL plan baseline by using the script file w9s4a. So what we're going to do is we're going to open this file. And what do I need is I need here the SQL ID of that hinted SQL statement. So what I'm going to do is going to pick up that SQL ID and put this over here. Then I will also need to enter that plan hash value. I'm going to take this plan hash value and I'm going to paste this as an argument for the parameter plan hash value. And then we also need to add the SQL handle for the original value. And this is something that you can find back over here in the script w9s2d. You have to take this original SQL handle and copy paste this over here. Just one moment. Make sure that you do the right copy pasting. So one moment, it was WSD, Control C, that one, and I do Control V, and I'm going to execute this, so this my SH connection, and execute this. And then what I'm going to do is that I'm going to verify if that second plan has now also been added as an SQL plan baseline by running the script file w9s4b. So that is this script file, sh connection. I'm going to run this. And I see for my original select statement index combined, I have now 2 execution plans. But the last execution plan that I've uploaded was an execution plan for that same statement, but that is using another hint. Now, if the original plan is not needed, then drop the original plan, option 1, from the SQL plan baseline, or fix the better plan to guarantee the plan for the next hard parse. Now, to choose for the first option, you're going to drop the original plan file and then execute this script file to check whether the original plan has been dropped. So what we're going to do is, so I'm going to take the script file w9s4c, via which we can drop an SQL plan baseline. So we need first to have the original SQL handle value being copy pasted into this location. So what I'm going to do is, I'm taking the original SQL handle, I say Control C, Control V. Plus you will have to enter the original plan name that you're going to drop. And you have to copy that value into that location. And the original execution plan is actually the second one that is being shown. The one that ends with 2E3. Yeah, you can verify this Just a moment. If you look at this script file, you see that the original execution plan ends with B2E3. Just one moment. So if I go back, I'm going to take this SQL plan name, go to C, and I do this. I'm going to choose the SH connection, and I'm going to run the script. And the original plan baseline has now been dropped. And I can verify this by running the script W9S4C1. So here W9SC41. I execute this, and I see only one plan is still loaded in the SQL plan baseline for that select statement using the original hint index combine. Then we need to test if the original SQL statement will be using that loaded plan. Now to do so, first we have to run this script to flush our shared pool. So we're going to clean it up for testing that step. So I have this script file, sh connection, and I execute. I do not have the necessary privilege, so do this then as the sys user and execute this. So now my shared pool is empty. Then what I'm going to do is I'm going to execute the SQL statements. So what I'm going to do is I'm going to use the script files W9S5B, B1 and B2. So first of all, what we're going to do is we're going to run W9S5B. So that is this one, where we're going to ask to perform the explain plan command for that original select statement called index combine. I say sh, I execute this, and you see that the SQL plan baseline is used for this statement, and you see that there is no bitmap merge being done because that is another execution plan than the one that he finds in the SQL plan baseline. So he will not be using that one, but he will use the one that is seen as a baseline plan. Then we're going to run W9S5B1. And what do you see is I'm going to execute that statement, and then I'm going to have a look inside the SQL plan baseline. I'm going to execute this, and you see that there are no rows being selected, as well as that there are no rows in the SQL plan baseline. And then we're going to execute the script file W9S5B1, where we're going to execute the select statement, and we're going to see that that execution plan, although not being used, is going to be uploaded into the SQL plan baseline because the automatic capturing of that execution plan or execution plans is active. So I'm going to execute W9S5B1. So here, there's that script file, execute the select statement and verify if that execution plan has been uploaded. Now what do I see is, okay, the select statement doesn't select any rows, but I see that the execution plan, although not used, is being uploaded as an SQL plan baseline, but which will be set to not accepted. So it will not be used because this is the plan that is using the bitmap merge, which had a cost of 4, while the plan that did not use the bitmap merge had a lower cost. And then you're going to execute this script file, W9S5B2, where you want to display that captured execution plan. And you have to look up what the original SQL handle is. I've already done that, and you're going to execute that query. And you see this is the bitmap merge execution, which was rendered by the optimizer, but it was not used, but it was captured, and I can view this by calling the function display SQL plan baselines. The only thing that you then need to do is clean up your environment. So you simply open the script cleanup09.sql, choose the SH connection and execute this. Well, to remove the plan baselines, do not forget that you have to type in the right SQL handle, and it drops table customers. Practices for lesson number 9, other optimizer operators. In the exercise of chapter number 9, you're going to use the result cache to improve SQL performance with repeated queries and examine the SQL statements that use other access paths. In the first activity of chapter number 9, you're going to explore the various possibilities of caching query results in the system global area. All the scripts that you need for this practice are located underneath the query result cache directory. First thing that you will need to do is you will have to run as sysuser the result cache setup shell script in order to prepare the environment for this activity. So what did I do on my practice environment? I've opened a terminal session, changed my directory to the query result cache directory, and launched the shell script result cache setup, which is going to create the user, the schema QRC, and which is going to create a table cache GFV and insert an amount of rows inside that table. Once you have done this, you're going to, in SQL Developer, you need to create a connection as that QRC user that was created by the previously launched shell script. So you go to your SQL Developer, and I've already made this connection QRC connection, but if I'm showing you the properties, so you can see here that I call it QRC connection. The username is QRC. The password is also QRC, and I'm connecting to my pluggable database as service ORCLPDB. You create that in exactly the same way as you have created the HR, the OE, the SH, and the sys connection in the exercises of chapter number 2. Now, as that QRC user, you're going to now determine the current content of the query cache by using the following statement, or open and execute the statement in the script file check result cache.sql, which is found underneath that directory query result cache. Now, what did I do is for this activity, I went into Tools, Preferences, I went to Database Nodes. There I picked the worksheet node, and I've changed the default path to look for scripts by SQL Developer to that query result cache. Once you have done that, you can then refresh your Files tab, and there you can then open this query result cache directory. And if you expand it, you actually see all of the necessary script files for this exercise. Now they're asking me to check now first the content of the result cache, and I can simply do this by calling the script file check result cache, where we're going to query then Vedal result cache object to see what is currently cached inside the result cache. And you're going to execute this as the QRC user. I'm going to execute this. And what do I see is now that currently my result cache is not empty. Now, it's stated in the activity guide that if the result cache shows some rows, you can then execute the following command in order to empty the result cache. So what do I have here is, I have here a worksheet where I'm connected as the QRC, and via this PL SQL calling the procedure flush of the package dbms result cache, you have the possibility to empty the result cache. So then if I go back to my script file and I'm going to execute this once again, you see now that the result cache is empty because I flushed the result cache with that earlier command. Then what you need to do is you have to execute the following select statement. You can copy paste this, type it in yourself, or you can open and execute query1.sql script file. So what I'm going to do is going to open this script file query1.sql, and what I'm going to do is execute this as the QRC user, and I'm going to auto trace this. And what do you see is that this statement is the very first time that I'm executing this select statement. And you see that its first execution took 1.482 seconds. Yeah, but the select statement has accessed those tables. Yeah, it does the join of the same table over and over, but blocks have to be uploaded inside the database buffer cache. The data needs to be scanned, data needs to be filtered out. But the result of that select statement is now also being cached inside the result cache due to this hint where I'm telling Oracle to cache the result of this select statement inside the result cache. So I can see in the execution plan, I can see that the result cache has been used, but the select statement is being executed traditionally. The first time, the result set is being placed inside the result cache. So because of that result cache in, the result of the query is computed using the result cache. Let's have a look at the content of the result cache. So what I'm going to do is I'm going to go back to this script file and I'm going to execute this select statement to view the content of the result cache. And what do I see is I'm seeing here that there is a result for this select statement being cached inside the result cache. I can see that over here. So you can see that the result of your query has been cached. Now what we're going to do now is we're now going to empty our buffer cache, because this select statement, it was executed one time for the very first time. Blocks need to be uploaded into the database buffer cache, the data needs to be scanned, and the data needs to be filtered out. And the result is returned to the application, but it's also going to be cached inside the result cache. Now what we're going to do now is we're going to now empty the buffer cache. You do this by the command alter system flush buffer cache. So here I go to this worksheet and I'm going to execute this command. So now my buffer cache is now being emptied. And then they ask me to rerun query1.sql. Now, the very first time that I executed query1, you see that it took 1.482 seconds to complete this query. Now I'm going to re-execute this statement. I'm going to auto trace, also ask to execute this. So I say auto trace, and you see that the result cache is being used, and you also see that the result is being returned in 0.169 seconds. That is because he says, yeah, but the result of that select statement is cached inside the result cache. So instead of accessing that table and performing those joins in the traditional way, in fact, I'm not going to do this. I'm going to get the result directly out of the result cache. So you see that the execution time for the query is now almost instantaneous. What we're going to do now is we're now going to insert a record into that table. So what we're going to do is, I'm going to insert one record in that table, cache GFV, and I'm going to commit this. I'm going to make this permanent. Now what do you have is, now this table has now one extra record. This means that the content of that table has been changed. Yeah, but that also means that the result of that previously launched query no longer reflects the state of the data inside that table. So we're going to determine again the content of this result cache. So what we're going to do is, I'm going to go back to this script file. And what I'm going to do is I'm going to execute this. Now what do I see is that the result that was cached for that select statement, that it shows now the status invalid, because the result is based upon the table cache GFV in fact, but the content of the table has been changed because I've added one extra record. So the thing is that if I would execute this select statement again, he will see there is a result for that statement cached inside the result cache, but I cannot use it because it does not reflect the state of the data in my table cache GFV at the moment. So the thing is, I'm going to rerun query1.sql. So I'm going to rerun this. I'm going to close this. Let's do the auto trace. And you see that it doesn't take 0.1697, but it takes 0.862 seconds. He cannot use the result that is currently cached in the result cache for that select statement because the underlying table data has been changed. So he has to access the table and its blocks again in the traditional way. So let's have a look now at the result cache over here. Going to empty this. I'm going to execute this. Now what do I see is that I have here my select statement again. You see that the result has been published. It actually has carried out the select statement again in a traditional way, uploading blocks in the buffer cache, accessing the data, filtering out the data, and that result is now being published inside the result cache. So again, it took some time to execute the query. The result cache shows that a new entry has been added for that new result. Now, you still see the previous result still invalid. The new result has been published and can be used. Now, what you can do is you have the possibility to get a detailed result cache memory report by calling the procedure memory report of the package dbms result cache. So what you can do is, so in my worksheet as QRC user, I'm going to set the server output on, and then I'm going to execute the procedure memory report of dbms result cache. I'm going to execute this, and there you can then have a look at the memory report of the result cache, and you can see how much memory can be allocated for the result cache inside the shared pool. Plus you also have the possibility to see how much memory has already been allocated for the result cache and how much of that allocated memory is now actually in use. Then we're going to rerun that query1 script file again. So it took 0.862 seconds, longer than before, because he has to refresh the result cache. But now if I'm going to execute that statement, again, you see, he returns the rows almost instantaneous, 0.121 seconds. Yeah, the query again uses the result that has previously been cached. Now you have the possibility to indicate that you would like to bypass the result cache when you're going to carry out select statements. Now what you can do is, so you can see here, by calling the bypass procedure of the DBMS results cache package, you can say, I want to bypass the result cache. I'm going to execute this. And if now I'm going to launch my query 1, and I'm going to auto trace this, you see that it took again 0.665 seconds, which is longer than when using the result cache. So the query again takes longer to execute because it no longer uses the result cache, because we asked to bypass the result cache. Now we're going to indicate that we no longer want to bypass the result cache. So what you're doing is you're going to put this bypass mode back to false. We can then rerun that query. I close my auto trace and I'm going to auto trace it again. You see 0.204 seconds, which is again lower than when we were bypassing the result cache. Then they ask us to execute this select statement. It's exactly the same select statement as in the script file query1.sql, except we do not use a result cache hint. So what we're going to do is we open query 2, we choose the QRC connection, and we're going to execute this. Now, as you can see inside the execution plan, that the result caching did not take place because I simply did not use the hint result cache as we have done in the select statement in the script file query1.sql. So although the query is the same as the one in query1.sql, it is not recognized as cached because it does not contain the hint. Now, how can we force that the previous query of script query2.sql will use the cache result without using any hint? Well, we can set the parameter result cache mode equal to force. Now we can carry out all of those commands by typing them in, or we use the force result cache script file. So I take here force result cache, open that QRC connection, and we're going to execute the script. So what you're getting is that the result cache mode is set to manual. I can look up what is currently inside the result cache. Yeah, I'm seeing that for this select statement using the result cache, that there is a valid result inside that result cache. But then at the end, the result cache mode parameter is being set to force. Then what we're going to do is we're going to execute query2.sql again, which is executing a query that does not use the hint result cache. So I take here query2, and I'm going to auto trace this and execute it. And what do you see is that the result caching is being used because the select statement is being carried out and the result of it is cached inside the result cache. You see that it took 0.324 seconds when I launch now my query2, but then if I'm going to rerun it again, you see it's only taking 0.152 seconds because it's using the result cache to return the result of that select statement. What we're going to do then is we're going to put the result cache mode back to manual. So here I'm going to type in the commands alter session set results now cache mode. I'm going to put it back to manual, and we're going to execute this. Then what we're going to do is we're going to clear the result cache. Yeah, we're going to call the procedure flush of the package dbms result cache. So what we're going to do is going to execute this begin block. I'm going to flush my result cache. And if I'm then going to look at the content of that result cache, you will see that it is empty. Then what we're going to do is we're going to create a function by calling the script createFunction.sql. This is a script that will create a PL SQL function that uses the result cache. So what I'm going to do is I say open create function, QRC connection, and I'm going to execute this script. So the function cachegfv_count has been compiled. We're going to determine what's in the result cache. So we're going to check again here, check result cache. We're going to execute this. It tells me no rows selected. It is still empty. What we're going to do now is we're going to call that function with b as its argument. So I'm going to go to my worksheet and I'm going to call that function with argument b. I'm going to execute this over here. I say execute and it returns me a result. Now it will take a long time to execute because the result is not cached yet. After executing the function's result with the b argument is placed inside the result cache. And you see that it took 1.121 seconds. But now I'm going to execute this again. Now what you see is that it now returns the result in 0.005 seconds. So at that time, with the second execution, the function executes almost instantaneously. Now we're going to call that function again, but with c as its argument. So what we're going to do is we take this, we're going to execute it with argument c, execute that statement, and you see that it takes 0.592 seconds. The thing is that select statement takes longer than the second run with argument b, because there is a new value for the argument. After the execution, that result where the argument is c is being cached. In the second activity of chapter number 9, you're going to explore the various access paths that the optimizer can use and compare them. You have the possibility of exploring 3 scenarios, each of which is self-contained. All of the necessary scripts are being found underneath the directory access path. First thing that we need to do is we have to make sure that you have an SH connection. Now you should already have one if you have made practice number 2. If not, please create with the provided information the SH connection. The first case of this activity is the so-called in-list operator. And what you need to do is, as the SH user, you're going to auto-trace the script mentioned in query08.sql file underneath the access path. So what did I do is, I went to Tools, Preferences, and changed the default path to access path, refreshed the files, and I have now here access to the access path folder in SQL Developer. And I need to open now query08.sql and execute this as the sh user and auto trace this. Now what do I see is in the execution plan that the inList operator has been used and that it's looking for those values via the index provisioned via the primary key upon the customer ID. And I also see that the cost is low in doing so. In the second case, you're going to use hash clusters. Now, before you can explore this case, you will have to set up your environment. What you need to do first is you will have to launch the script file shcsetup.sql, which is going to create a big M fact table that is a member of the big M cluster object. Yeah, the big M cluster is a single table hash cluster. And also the rows of the table big M fact, which are using the space of big M cluster, will be sorted upon department number and the salary column. So setting up your environment for case number 2 is that I've changed in a terminal session my directory to access path. Then I started up SQL Plus, but I do not ask to log in, and to execute the script sorted hashcluster underscore setup.sql, which is going to create the user shc plus is going to create the cluster big M cluster, and the table big M fact will store its data in the space provisioned by the big M cluster, and the data of the big M fact table will be stored in the big M cluster physically, sorted upon department number and salary column. And then a tremendous amount of records are being inserted into that table, and optimizer statistics are being collected for the objects in that newly created schema shc. So this is in order to prepare the environment for case number 2. Then what you need to do is, in SQL Developer, you will have to establish a connection as the shc user, using the information as indicated in the activity guide. Now, I've already made up this shc connection, and just to show you that, these are the properties. So the connection name is shc connection, the username is shc, the password is the same, connecting to pluggable database ORCL PDB. You can test this first before you're going to save the connection. I'm simply going to cancel over here. Then what you need to do is you will have to execute query15a.sql script, which is going to set the work area size policy to manual and the sort area size to a small value. Because there's a lot of memory available upon your practice environment, this script will reduce the amount of memory available to your session. It will then also empty, flush the buffer cache as well as the shared pool to eliminate the possibility of the cost being reduced by previous queries loading the cache. So, in my file step, I'm going to search for query15a, open this and execute this as the shc connection. Execute this, and this is now being done. Then what I need to do is I have to auto trace the query in script query15b. So I go search for query15b, open this, set shc connection, and do the auto tracing. Now what do I see is that I'm looking into my big M fact table, which is a table that is making use of the big M cluster to store its data. And you see it in the execution plan to obtain all the records of the big M fact table where department number equals 10, that he can make use of this sorted hash cluster. It's going to scan that sorted hash cluster. Also, you will see that the cost is 1, which is a very low cost to obtain the data out of the big M fact table where department number is 10 by scanning the sorted hash cluster. Then we're going to reset our environment again. So we're going to execute this script again, like this. And then they ask you to look at the query in query16.sql script file. So I'm opening that one, shc connection, and perform the auto tracing, where I'm doing exactly the same query as before, but I'm asking to order the result upon salary. And again, he's using the hash cluster to obtain the data. The cost is still 1, although you're asking to do a sorting. Yeah, but we have asked that the data of the big M fact table using the space of the big M cluster, that data is sorted upon department number and per department number upon salary. So again, a really low cost. So it's a slightly different query, one that requires ordering the result based upon the sorted cell column. You can still use the cluster access path without having to sort the data, and the cost is still minimal. Then we have to reset our environment again by launching query15a.script file. And then they ask me to look at query17.sql. And what I'm doing over here is that I'm asking all the records of the big M fact table where department number equals 10, but sort the result upon salary in descending order. Set my connection, do the auto tracing, and although the data is sorted in the big M fact table using the big M cluster space upon department number and per department number upon salary in ascending order, can still make use of the big M hash cluster to scan it. No sorting is required, although I'm asking to have it sorted in descending order, and I still have simply a cost of 1. So the optimizer can still use the cluster access path without having to sort the data. The cost is still minimal. Then, after resetting my environment, I have to look at the query in the script query18.sql. So first of all, reset my environment, open query18.sql, set my connection to shc connection, and then I'm accessing that cluster table where department number is equal to 10, but I'm asking to sort the result upon a non-clustered column, in this case the employee number column. And I'm going to execute this. You see that it takes a little bit of time. And what we will observe is that it can still use the hash cluster, but that there is an additional order by that needs to be done that increases the cost tremendously to carry out that select statement. So you can see that here that it's still using the hash cluster to access the data where department number equals 10. That's a really low cost, but the sorting upon a non-clustered column increases my cost tremendously to carry out that particular select statement. Then reset our environment again, and we're going to auto trace the script query19. So I'm going to reset this, reset my environment, execute query15a script again, open query19.sql, accessing my cluster table, department number is 10, but order upon the sorted column salary and also upon employee number. Setting my connection, do the auto tracing. And what we will see is it can still use the hash cluster, But once again, because I'm asking to sort upon a non-clustered column, it's going to increase that cost tremendously. The third case of this chapter number 9, activity number 2, is the utilization of the index cluster. Now, the Nick setup script file was already executed as part of the setup for this practice. This script creates and populates the Nick schema to set up your environment. So it has already created an emp and a dep table, two separate tables, and each table has an index upon the department number value. If this setup was not launched yet, then simply in a terminal session, type in sql+/nlog at nicksetup.sql. Also, they ask you to create in SQL Developer a connection as the Nick user, which I have already done. So I have here Nick connection, show you the properties. So the name is Nick connection, username Nick, password Nick, connecting to pluggable database ORCL PDB. And then as a Nick connection, you have to execute the script nickquery.a.sql, which will set parameters, sort area size and hash area size to a small value. So I'm going to look for Nick query A. Make sure that we use the Nick connection and execute this. Session has been altered, work area size policy, sort area size parameter and hash area size parameter have been set. Then you have to auto trace the query in Nick query B script file as that Nick user. So I'm going to look up Nick query B. I use the Nick connection and I'm going to auto trace. And what we're doing is that we're doing a join between two physically separated tables, emp and dep, join upon department number. We're going to auto trace this. Now, what do I see in the execution plan? That it can make use of the index upon the department number column of the dep table, as well as the index upon the department number column of the emp table to perform the join. That's what I'm seeing within the execution plan. So the optimizer is able to make use of the index to resolve the join. But how can we enhance the performance of this previous query? That's actually by putting the two tables inside a cluster. So we still have the concept of having two separate tables, emp and dep, but they both will use space of one and the same cluster object. And the rows of those tables are stored together in the cluster based upon the department number value. If you did not run the setup yet, you can launch ecsetup.sql script file to create the index cluster, the two tables emp and dep, that store their rows inside the cluster, but clustered around the department number column values. I've already launched this script file. Also, they ask you to create in SQL Developer a connection as the IC user. I've already done that as well, so I have here my IC connection. Go to properties. So the name is IC connection, username IC, password IC, connecting to ORCL PDB. So I've already made this connection. If not, create it with the specifications mentioned in the activity guide. Then what you need to do is you have to run nickquery.a.sql, but now as the IC user. So you go to nickquery.a.sql, but make sure that you now execute this script as the IC user. Then what you need to do is you're then going to auto trace nickquery B as the IC user. So I take my nick_queryb script file, change the connection to IC connection, and I'm going to auto trace this. And what do you see is that he's accessing the cluster object using the index app_depth index that has been created for this index cluster, and this will improve the performance of this particular select statement. So the optimizer is able to use the cluster access path that makes the query execute faster. Now this is the end of the 3 cases in this activity number 2. Now what they're asking you now to do is that you're going to close all the connections to the SH user. So check your terminals. If there are still connections open as the SH user, well, close those SQL Plus sessions. Also make sure that in SQL Developer that you disconnect the SH connection. And then what you will need to do is you will then in a terminal change your directory to access paths, and you're going to run this shell script in order to clean up your environment for this practice. It will rebuild the SH schema. If the user drop message does not appear or there's another message in place of it, wait until the script finishes, find an exit from any sessions that are connected as the SH users, and execute this script again. So do not forget to do this access path clean up of the environment.